Okay, so using the Kf and Kb equations, Kf and Kb are constants. Basically, Kf is for the molar freezing point depression constant, and Kb is for the molar boiling point elevation constant. So the thing you've got to remember about colligative properties of solutions versus solvents is that boiling points of solutions is elevated compared to that of the pure solvent. So BP of solution is higher than BP of pure solvent. So I'm going to call that T0, the pure solvent. Let's go with that. Boiling point of solution, we're just going to call that T BP, like so. So freezing point depression is the same kind of phenomena, but at the other end of the scale, that a solution is going to freeze at a lower temperature, which is why salt is able to melt ice on roads, right? Elevation, BP, sorry, freezing point of solution. So we can call that TFP is lower than freezing point of pure solvent. So we're going to call the pure solvent T0 as well. Freezing point. Let's differentiate between those. So we can write some expressions to describe that. So the difference between the boiling point of the pure solvent and the solution, you're going to have to add on the difference, right, in order to work out the boiling point of the mixture. So the boiling point of the mixture is going to be equal to whatever the boiling point of the pure solvent is, plus whatever the difference is. So we're just going to call that delta T, the boiling point. So I'm going to put a little delta symbol in there like so. Possibly. Let's see if I can make one. So delta means the change, right? So you've got to add in the difference between the pure solvent and the solution in order to work out the boiling point of the solution. So same kind of logic with the freezing point of our solution, except of course you're going to subtract off the difference between the freezing points because the solution is going to freeze at a lower temperature. So I put my little delta in there. Might look kind of janky, but we'll do our best. Okay, so those are the expressions that we're going to be using. The KB and KF expressions are just going to be relating to the difference in temperature for both of them. So delta T for the boiling point, we can calculate that by taking the constant, which is Kb, times the molality of that solution. So let me just put delta T BP. That is going to be related to the constant. So Kb is the boiling point constant times the molality, okay? And it's essentially the same equation for freezing point, okay? So the change, the difference between temperature of the freezing point of the solution and the pure solvent is going to be Kf, so a different constant, the freezing point depression constant times the molality. So you're going to take the same kind of approach regardless of which one you're being asked about. So the important difference is knowing the difference in definition of boiling point elevation versus freezing point depression. I've just realized I've written elevation because I'm a numpty. This is talking and typing. That's not supposed to say elevation at all. It's supposed to say depression is the word that we're going for. So depression. Okay, so that's supposed to be in there. Can I do an arrow? Yes, I can do an arrow. Look at that. Beautiful. We can find beauty in things being messy. Okay, so we've been given that our substance condenses at a temperature of 99.6, and then if it has urea dissolved in it, it condenses at 102.4. So we can work out our delta T for our boiling point, for our elevation. So just to make it super clear, for our pure solvent, our temperature for the boiling point would be that lower one, the 99.6 degrees Celsius, and our higher boiling point for our solution would be that 102.4 degrees Celsius. So now we can work out our delta. Our delta T for the BP is going to be my TBP minus my T0 BP. And excuse me 1 minute, because I'm going to have to write that delta in a minute. So 102.4 minus 99.6 is going to give me a difference in terms of degrees Celsius of 2.8 degrees Celsius, which let's point out quickly, that's the same as 2.8 Kelvin, because the difference in a degree Celsius is the same as the difference in degree Kelvin. The size of a degree is the same in Celsius and Kelvin, just that they have a different 0 point, a different start point. So you can save yourself some time. Any question where it's a delta T, you don't have to worry about converting between Celsius and Kelvin. Okay, so we've got that sorted. And then if we are being asked to solve the molar boiling point elevation constant KB, that means we're going to need to rearrange. Why am I pointing at my screen? We're going to need to rearrange and solve for KB. So KB is going to be delta T BP, which we have already calculated, yay go us, divided by the molality. So for whether you're dealing with boiling point elevation or freezing point depression, you are going to have to deal with calculating molality. So remember, molality is another way of defining concentration. It has the symbol little m. Not confusing at all, right? Molarity versus molality, only one letter difference. Abbreviation big M in italics versus little m in italics. What could possibly go wrong? So that is defined as the number of moles of your solute divided by your mass in kilograms of your solvent. Okay, so the units of molality are going to be moles per kilogram. So we can calculate that. So we're going to have to work out our number of moles of our solute, which is our ammonia. So molar mass of ammonia is about 60.06. So if you're not sure how to calculate it, we've got 2 nitrogens, so 2 times 14.01. We've got 4 hydrogens, so 4 times 1.0079, 1 carbon, so plus 12.011, 1 oxygen, plus 15.999, should come to about 60. So we have 26 grams. Would help if I could type 26 grams of ammonia. We're going to use that molar mass as a conversion factor. So I like to recommend that if you find that a little bit confusion, always write it out as an equivalency first. So for every 1 mole of ammonia, it weighs 60.06 grams. Some people find that a little bit less confusing than using the units of grams per mole. So now I know to cancel out, I'm going to put my 60.06 grams on the bottom and my 1 mole of ammonia on the top. So that's going to give me units of moles, and that comes out to be moles. How many moles? 0.4329 and friends, moles. Okay. So I've got my moles of ammonia. So now I should be good to calculate my molality. Again, I've been given my mass of my solvent as 300 grams, and we define molality in kilograms. So what I need to do is take my number of moles of solvent, 0.4329 moles, divide by the mass in kilograms. If I don't have it, I can just use unit conversion. So I should know by now that 1 kilogram is 10 to the power of 3 grams, or 1,000 grams if you prefer. So I can just add my unit conversion straight in there to save space. So let's just check. My gram should cancel out, and that should give me units of moles per kilogram, which is my definition of molality. And that should come out to be 1.443 moles per kilogram. So then I can substitute in and solve for KB. So I already got delta T was 2.8 degrees Celsius. I'm going to divide through by the 1.443 units of moles per kilogram. So then my units are going to be Celsius per mole per kilogram. Gets a bit messy, right? So that will be equal to 1.9. And that's going to be Celsius per mole per kilogram. I'm not sure how ALEKS would prefer you to write that. It might want you to write, let's see, it might want you to prefer to write like Celsius kilograms per mole, something like that, or just use to the -1 or whatever. Huh. Are you recording? Yes, we're still recording. Okay. So let me tidy that up. So I need to put that line in there. So 1 over kilograms, I can tidy that up a little bit. That'd be 1.9 Celsius per mole, so mole to the -1 if we're being strict, and then kilograms. So that would be preferable. Also would be equivalent to say Kelvin per mole kilogram. That would be fine. Okay.